This interview is part of InterPore's Time Capsule series. We often recognize the pioneers of our field for their scientific contributions, their groundbreaking research and technical achievements. But we rarely have the opportunity to learn about the personal history, motivations, and philosophies that shape their work. Today, we have the distinct privilege to be speaking with Professor Norman Morrow, a towering figure in the field of wettability and interfacial science as applied to porous media and the subsurface. He's a member of the U.S. National Academy of Engineering, a foreign member of the Russian Academy of Sciences, honorary professor of Xi'an University of Petroleum, and visiting professor at the Australian National University. He received the 1996 Technical Achievement Award from the Society of Core Analysts. He authored 2 distinguished author papers and served as distinguished lecturer for the Society of Petroleum Engineers and received an Enhanced Oil Recovery Pioneer Award. His work has received many other awards and accolades. His pioneering research has profoundly shaped how we understand fluid behavior in complex geological systems with implications for oil recovery, reservoir engineering, energy systems, and beyond. Professor Morrow's career began with a Bachelor of Science with honors in chemical engineering and a PhD in mineral engineering from the University of Leeds. His journey took him across premier institutions and industry research centers, including Columbia University, Humboldt Oil Research, the Petroleum Recovery Institute in Canada, Petroleum Recovery Research Center and New Mexico Tech, and the University of Wyoming. At UW, he held the prestigious Wohl Chair of Energy and served as a distinguished scientist at the Western Research Institute. Over the course of his prolific career, Professor Morrow taught 45 courses, supervised dozens of graduate students, hosted visiting researchers from across the world, secured patents, and published nearly 200 technical papers. His insights into capillarity, wettability, spontaneous imbibition, surface chemistry, and petrophysical characterization have left an indelible mark on both theory and practice. Today, we have the opportunity to reflect on this extraordinary journey and to hear, in his own words, the experiences, ideas, and challenges that shaped a career of enduring impact. Professor Morrow, thank you for agreeing to this interview and for sharing your experiences with us.
Well, thank you for your generous introduction, Simone, and for this opportunity to reflect on my life and career in research.
You began your academic journey at the University of Leeds. What initially drew you to the field of porous media and interfacial science?
After graduating in chemical engineering in 1959, I felt a need to focus and was attracted by research. I was awarded a graduate scholarship in minerals processing for work on the removal of water from fine coal.
What was your introduction to research?
My research advisor, Colin Harris, had settled on techniques developed by W.B. Haynes in the late 1920s.
Did you apply surface science and mineral engineering studies to your work?
Yes, many developments in interface science arose from studies of selective flotation of minerals by attachment of air bubbles. My first investigations of wetting and capillarity drew on contact angles data for xanthates adsorbed on galena. Capillary pressure hysteresis data for packings of galena particles were extended to variation in wetting by adsorption of xanthates of different carbon chain lengths. In contrast to a common assumption that capillary pressure was proportional to the cosine of the contact angle, the pressures for drainage of galena particles were barely affected by contact angle. And then, even more surprising, the imbibition pressures were reduced far more than expected.
You were at Columbia University in 1963 and 64. What did you work on during that time?
I was interested in the thermodynamics of capillary pressure hysteresis and first investigated the fine details of the buildup of retained liquid, commonly referred to as the irreducible minimum saturation. The irreducible saturation arises because of hydraulic isolation of the wetting phase during the course of drainage. For example, for pendular rings at sphere contacts in packings of ball bearings, I determined their pressures from dimensions shown by mild etching with dilute hydrochloric acid. The retained wetting phase configuration scaled directly with sphere size. Pressures of the hydraulically isolated wetting phase retained as pendular rings or partial rings were calculated from the diameter of the etched lines of the lines of contact on the spheres. The data enabled equilibrium saturations that would obtain if all retained liquid surface curvatures were equal. Well, the figure on the left shows a pendular ring suspended between two spheres, and there's a capillary pressure curve shown, and the curve on the left-hand side shows the buildup of the disconnected fluid as you raise the pressure in the system. Now, if you took every pendular ring and took it to the pressure that you were observing on a manometer, then the drainage curve, it would not show an irreducible saturation. It would show a decrease in saturation as the curvature gets higher. Common interest in capillary action in porous media led Jim Melrose, Mobile Research, to visit Colombia. The photograph shows Colin Harris to the left, Jim Melrose to the center, and I'm to the right. Jim became a great friend and mentor.
It's an amazing story. And you did so much to understand capillarity at a fine level. And I'm curious, how did these experiences understanding capillarity connect with practical questions related to the petroleum industry?
One application of capillary pressure data by the oil industry was determination of how much connate water was retained by hydrocarbon reservoirs in association with the oil. Issues arose with reservoir engineers and log analysts as to the fundamental nature of so-called irreducible saturations that result from loss of hydraulic conductivity. Here we have an example of capillary pressure curves that exhibit very distinct irreducible saturations. Empirical correlations between irreducible saturations and electrical conductivity used in log interpretation are based on some form of laboratory drainage data. However, many oil and gas reservoirs have geologic time to achieve capillary equilibrium as set by the height in the reservoir. I believe restoration of water saturation in laboratory cores to a distribution that corresponds to the saturation and distribution of connate water retained in oil and gas reservoirs is an unsolved problem.
Now, capillarity is undoubtedly very closely coupled with wettability, but your early work was focused on understanding capillarity. So I'm curious, how did you return to the question of understanding wettability?
Well, during my time at Columbia, as part of a search for means of wettability control, I visited the Naval Research Labs in Washington. Reproducible contact angles ranged from 0 degrees for pentane to 108 degrees for water. My first use of Zisman fluids at Humble was to investigate the effective contact angle for drainage of PTFE sphere packs in a general investigation of factors that determine the magnitude of irreducible saturations.
Thermodynamics provide a very powerful tool for analyzing and understanding physical systems. And your early work laid the groundwork for thermodynamic analysis of capillary action, in particular in porous structures.
Application of classical thermodynamics to capillary pressure hysteresis in porous media hinged on justifying the use of capillary pressure data to define reversible work. The loss work for drainage, or the loss-free energy for imbibition, results from spontaneous jumps in fluid distribution. Cycles of spontaneous disconnection and reconnection of the wetting phase and the non-wetting phases determine the lost work as defined by reproducible hysteresis in capillary pressure versus saturation data. Now you see a capillary pressure hysteresis loop that features isons and rheons for drainage and imbibition. And when there's drainage, there is disconnection of the non-wetting phase. And when there is imbibition, the wetting phase reconnects. But now the oil is trapped during the imbibition process. So we end up with 3 simultaneous cycles of pressure change, trapping and non-trapping, and for the 2 phases. Novel techniques for the first reported measurements of interfacial areas in porous media are shown, and they showed that the conversion of work to surface-free energy for drainage was much less than the conversion of surface energy to work for spontaneous imbibition. So that is a thin section where I drained a wetting phase epoxy, then injected an orange epoxy, and then made thin sections, and then I did analysis of the saturations from point counts and the surface areas from line cuts. Now, there's a much more difficult task of determining capillary pressure and associated changes in interfacial areas for sandstone and carbonate rocks. And that was achieved many years later by graduate student Sid Seth. The data showed loss work for drainage versus imbibition increases as the ratio of the pore body to pore throat size of the porous medium increases.
And by this point, you'd done so much, looking at capillarity, wetting, looking at cycles of spontaneous disconnection, reconnection of various phases, looking at the thermodynamics of the problem. But then you moved to Canada.
Yes.
When did you move to Canada?
1969, I joined the Petroleum Research Institute in Calgary. The Petroleum Research Institute was housed in the Chemical Engineering Department at the University of Calgary. The chance of working on wettability in an academic environment was appealing.
What approach did you take to investigate wetting?
Well, Zisman and co-workers' liquids were used to determine effective contact angles at rough surfaces. The effective angles were determined from capillary rise in internally roughened tubes. Extensive measurements of receding and advancing contact angles for a series of Zisman et al. Liquids acting in internally roughened PTF tubes showed remarkably consistent trends. Significant effect on both the receding and advancing contact angles, but they were highly reproducible under a wide range of circumstances. So what you see here is the advancing and receding angles plotted against the contact angles that were measured at a smooth surface.
Receding and advancing contact angle is, I think, a fascinating problem, especially it couples very interestingly with surface roughness, and in porous media it becomes even more complicated. So how did the behavior you observed fit with interface behavior in porous media?
Well, the first thing we had to do was make a suite of porous media of differing porosities and permeabilities. And for that we used Teflon particles, and we used a combination of compression and heating to make Teflon cores. And we made drainage and imbibition measurements for a series of Zisman liquids, and they showed very little reduction in drainage pressures, but very large reduction in imbibition pressures. Now, this is after 4 years of measurement, maybe. To a first approximation, drainage pressures were proportional to the cosines of receding angles, and imbibition pressures were proportional to the cosines of the advancing angles. And these angles had been determined independently for rough surfaces. Geometric effects of pore shape were actually secondary. In the figure, we've got the angles for the rough surfaces there, and also superimposed the advancing and receding angles determined from the change in capillary pressure for several types of porous media. And this data is smooth, but it matched very closely the receding and advancing contact angles measured for the tubes, which means that the effect of pore geometry is secondary.
So from your time at Columbia, moving to Western Canada, there's continuity in your work, and you were making amazing progress. But then you moved again. You moved to New Mexico. Why did you move to New Mexico?
In 1976, Joe Tabor called to say he had accepted a position as director of a newly formed Petroleum Recovery Research Center at New Mexico Tech. The move to New Mexico in 1976 provided great opportunity for career development. There were numerous pluses to joining the center. Joe worked directly with the architect on the design of a beautiful fit-for-purpose building. Laboratory space would be ample. As an adjunct professor of petroleum engineering, I would be encouraged to work with students and also enjoy many of the normal privileges of academic freedom, such as collaboration and choice of where to present and publish. Startup funds were adequate. Funding was structured so that external support brought in by winning proposals would be matched by the state of New Mexico.
Any center is bound to need external funding, and that's a very important part of any research enterprise. What work did you propose that first gained outside funding?
The first major funding award concerned the mechanism of entrapment and recovery of residual oil. A common working assumption by most of the industry was that all reservoirs were strongly water wet, and this was optimum for recovery. Our first studies focused on the detailed mechanism of entrapment and mobilization at strongly water wet conditions. John Chatzis joined me at PRRC in January 1980. He made key contributions to the mechanism of residual oil trapping and mobilization in micromodels and sandstones. Significant improvements were made in micromodel design and manufacture. One of the patents appeared on the cover page of the April 1983 Society of Petroleum Engineers Journal.
Now, how did your work on recovery from crude oil, brine, rock combinations get started?
Hal Lim was a master's student, investigated recovery of crude oil from Berea sandstone, an industry standard rock used in numerous studies of oil recovery. Water flood recoveries compared to results for strong water wetting were surprisingly high, even at breakthrough. Rates of recovery of crude oil by spontaneous imbibition demonstrated weak water wetness. Brine permeabilities at water flood residual were low. Complementary micromodel studies were made that showed efficient recovery. Oil tended to be recovered from pore bodies, but retained at pore throats. The results were an encouraging start to parametric studies aimed at unraveling the key factors that control the recovery behavior of COBR combinations.
Now, this is around the time that Jill Buckley enters the picture. You knew her beforehand, right?
Yes, she was working at the center.
Right. And so when did Jill join the group?
She expressed interest in working on wettability and joined the group in 1983. Starting with contact angle adhesion tests with Moutray crude oil, Jill made major contributions to many other COBR studies. She gained international fame for unraveling relationships between crude oil chemistry, surface activity, phase behavior, and wetting.
Now, building on the collaborative work that's developing during this time, impactful, very meaningful, deep, fundamental work. How did you follow up on the work with Moutray crude oil?
Well, oil companies showed increasing interest and support for our work on COBR water flood recoveries, backed by wettability behavior, as shown by spontaneous imbibition. Statoil provided a barrel of North Sea oil, ST86, and Berea Sandstone 500 was again the test rock.
All this success undoubtedly had something to do with the development of the PhD program. When did the PhD program in petroleum engineering get started at New Mexico Tech?
Well, it got started in 1986, and Pooji Jadanandan was my first PhD student. He investigated oil recovery for wettability states induced by Moutray crude oil used in earlier studies and the ST86 oil. Imbibition rates and oil recovery were sensitive to systematic changes in brine composition for Moutray crude, but not for ST86. Puji's work provided the largest body of data yet reported for water flood recoveries versus wettability. The results show a distinct trend with recovery being maximum on the water-wet side of near-neutral wettability.
You wrote a review paper in 1990 titled Wettability and Its Effect on Oil Recovery. That paper is one of the most highly cited works in petroleum engineering. What insights led to its development, and why do you think it resonated so much with the community across the world?
The SP Distinguished Author Papers are intended to provide a short summary on a selected topic. They reach a wide audience. The paper included the distribution of residual oil saturations measured worldwide by single well tracer tests. The parametric test for water flood recovery on Mukche crude oil, together with other data showing maximum oil recovery on the water-wet side of near-neutral wettability, also attracted significant attention.
This is around the same time that you started with Jill Buckley a symposium series on reservoir wettability, and that's something that's touched my life personally. And it's still being held every 2 years. How did it all begin?
Well, by 1990, it was time for us to present our first project review. Jake Rathmell inquired about the possibility of presenting recent work from ARCO. So opportunity was then offered for other industry supporters to also present. All accepted.
Were you surprised?
Yes. And the project review was elevated to the status of an international symposium by a DOE official.
Now, speaking of internationalization, over the years, you've hosted over 50 visiting researchers. What role did those collaborations play in shaping your scientific thinking and research direction?
The contribution of visiting researchers in scope and research productivity were huge. And when I think back, totally unanticipated. The visits began after I received a fellowship in 1977 from the Commonwealth and Industrial Research Organization to work with soil scientists in Canberra. Ian White at CSIRO then spent a sabbatical year, 79 to 80, in the newly opened Petroleum Center. Vladimir Horner from the University of Ottawa and Jeff Mason from the University of Loughborough both spent sabbaticals at PRRC from 1981 to 1982. Vlad studied surfactant recovery mechanisms, including the effects of gravity. Collaboration with Jeff Mason lasted over 30 years, producing over 40 publications.
Now, was it right around this time after your sabbatical that you got involved in low permeability gas sands at PRRC?
No, it was before then. The DOE project officer for our work in oil recovery told us of a pressing need for long-term fundamental work on low permeability gas sands. The first subject we addressed at PRRC was that even though porosities of the sands were very low, typically 6 to 8%, gas permeabilities were remarkably sensitive to overburden pressure. I invited Kay Brower, a professor of chemistry who worked on chemical reactions at very high pressures, up to 30,000 pounds, to collaborate. Other studies included novel petrographic work on pore structure. This inspired the cover page of the April 1985 SPEJ. In the energy field, the production of gas and oil from tight sands and shales in North America has gone from what many viewed as an unrealistic endeavor to a major increase in hydrocarbon reserves, which have contributed to the nation's self-sufficiency in energy.
So from Leeds to Columbia to Calgary to New Mexico, and yet another move to University of Wyoming, which is where we are today. At PRRC, you had developed collaborations, you had many exchange visitors. Did that experience continue?
Jeff, Jill Buckley, and Koichi Takamura became very frequent visitors to UW. Our sabbatical visitor was Agnello Manella, first sabbatical visitor. In 1993, and he was on industrial leave from any recherche in Italy.
How was your work at UW initially supported?
Well, proposed research at UW on recovery of crude oil gained growing interest and funding. Obtaining data for other COBR combinations was considered the best way forward. Support initially came from industry and from UW through the Enhanced Oil Recovery Institute. In addition to financial support, industry made essential contributions of crude oil, usually by the barrel, from reservoirs of interest. ARCO provided a barrel of crude oil from a new, uncontaminated well, Alaska 93. The petroleum engineering laboratories became a hive of activity.
What other funded projects did you work on?
In 1993, in response to a DOE call for proposals, a joint project with Jill Buckley, who now ran the group at PWRC, entitled Wetting Behavior of Selected Crude Oil Brine Rock Systems, was funded. Many companies showed interest in participation. Concurrent with the low salinity work in 2002, we again teamed up with Jill at PWRC for two other proposals, one on Arctic drilling fluids and the other on oil recovery from fractured carbonates. Steady progress was made in both areas. During 2004 to 2005, 5 PhD students graduated in petroleum engineering. Jason Tong and Hong Wen Tia worked on various aspects of recovery of crude oil from sandstones and carbonates. Herbert Fisher obtained a very large data set for spontaneous imbibition. The set became the basis for several advances in the scaling of imbibition data. Sid Seth measured interfacial areas for sandstone and carbonate and also spent time at Arnie Grauer's laboratory at the University of Bergen to obtain specialized capillary pressure data. In 2003, the DOE issued a call for a long-range project on fundamental studies of spontaneous imbibition. The call was a perfect fit for ongoing work. We had already published extensively on scaling of imbibition data for strongly water-wet systems. Highly productive collaborations were ongoing between the UW group and Jeff Mason at the University of Loughborough, Doug Ruth at the University of Manitoba, and Martin Furneaux and Osmond Haugen at the University of Bergen. Arnie Grauer supported numerous visits by researchers and students from Bergen and encouraged connections with Phillips Petroleum in Tulsa. The effort eventually led to over 30 publications.
Now, the results obtained during this work at University of Wyoming raised the possibility of enhanced oil recovery by low salinity flooding, which is started all from here. You're the singular pioneer of that, and it's led to its application at the field scale in many places. How did that breakthrough come about?
Tom Tang observed increase in recovery with decrease in salinity for 3 crude oils: Alaska 93, Dargang crude, and CS crude supplied by BP. In tests initiated by Cliff Black at BP, similar trends were found for crude oils and reservoir cores. At UW, reservoir cores provided by BP showed higher response than Berea 500. The low salinity work at UW received increasingly strong support from industry. Our DOE support grew after teaming up through Charles Thomas with INEEL at Idaho Falls and Oak Ridge National Laboratories. Results continue to be highly encouraging.
And I've heard and read papers and I've heard talks, various people describing the mechanisms. And in your opinion, what is the mechanism of increased oil recovery by low salinity water flooding?
You may be ahead of me now.
I don't think so.
I have not followed much of the literature since retirement in 2015. There are now almost 10,000 citations of our low salinity papers. However, I understand this question is still largely open.
You authored with Jill Buckley a distinguished author paper in 2011 on low salinity. What was the main conclusion of that paper?
We pointed out that much remains to be learned about the effect of injection brine composition on oil recovery for COBr combinations. The paper concluded with identification for the sufficient conditions for the low salinity, we called it LSE effect, and understanding the circumstances under which there was little or no LSE effect remain as outstanding challenges.
What did your last students work on?
In my final years, 4 more PhD students graduated. Nina Loahajo, Suluni Ramathalika, and Hu Pui works on various aspects of increased oil recovery, either by cyclic or the final PhD student, Baruz Raisi, published fundamental work on the effect of pore shape and surface roughness on capillary properties. Baruz also measured extensive hysteresis data for 3 types of sandstone. He identified key parameters of pore structure by tuning network models to fit the hysteresis loop. Nina and Minoto, both brilliant researchers, stayed at UW in postdoctoral positions until 2014. Final studies related to the Macondo oil spill of 2011 in the Gulf of Mexico included work with Koichi on the spreading and retraction of crude oil on seawater. Carol Robinson, the group secretary, a wonderful calming influence who held everything together for 16 years, retired in 2014 and moved to France. At 78, it was high time for me to retire. I had moved on to other interests, especially duplicate bridge, and am thoroughly enjoying life in New Mexico.
After retirement, since retirement, have you been involved in any other developments in the area?
Yes, but only indirectly. Plans for inclusion of desalinization plants on offshore platforms were proposed. However, there may be many lower-cost sources of low salinity brine. After retiring in 2015, I learned that Mike Pearson, a renowned hydrologist at New Mexico Tech, was participating in a major NSF project in which a drilling ship investigated continental shelf resources. They produced a map that showed low salinity brines in offshore sands around the world. Some of the sands, for example, off the west coast of Africa, were in the same area as major oil fields. A paper on the relevance of these discoveries to low salinity flooding was published in 2017 in the AAPG Bulletin. In looking over low salinity papers that have appeared over the last 8 years, the paper has not gained much traction, having only been cited 17 times. An overlay of the offshore low salinity sands with locations where residual oil had been determined by single well tracer tests available on Chemical Tracers Inc. website would make a start to arousing interest.
Now, you had a long, highly impactful, very productive career. Reflecting on that career, what has given you the greatest satisfaction? Scientific discovery, mentorship, collaborations, or something else?
Well, here are a few things that I find highly rewarding. Starting from an idea to seeing experimental data accumulate to tell a consistent story, sharing a student's excitement and motivation in the course of gathering data, participating in collaborations that were key to achieving a successful outcome. The work often involved access to various types of high-cost imaging and other equipment. Seeing work such as low salinity flooding being built on by other researchers, meeting researchers in person after becoming familiar with their work from publications, and hearing that ex-students are enjoying successful careers is always pleasing.
Yes, it is. How would you like your scientific legacy to be remembered?
Publications provide a permanent record. Papers that contain sound theory and/or data and can be readily reproduced serve best as a strictly scientific legacy. Citations and research that builds directly on your work is remembrance. Jeff Mason considered citations to be a measure of legacy. Continued citation of early papers over many decades indicates that work has gained lasting recognition.
Well, thank you for these recollections of your life in research. And Norm, I am thankful to you. I admire you as a person, as a researcher, and I appreciate and I'm greatly thankful to you for your mentorship and your wisdom. Thank you so much.